Welcome to my channel. So today's topic of discussion is rocket ship reentry. And I'm putting ideas out. I'm not saying I'm right or that I'm correct in any way. The reason I'm putting the ideas out is because someone else needs to counter the idea with a better idea. This is not about trashing my ideas, because my ideas may not be correct. What it is to get you to think about different ideas and to see if you can come up with better ideas. Without us working together on this, it's going to be really difficult to achieve. So, a couple of the things I was thinking about with reentry has to do with the geometry of the ship. And the turbulence of reentry and the lack of atmosphere until it gets to a point where there is atmosphere. And I'm going to use the soda bottle as the ship, and we're going to use smooth swales as the planet, just because it's there and it's kind of roundish. The descent of the ship in towards the planet through the atmosphere has a specific angle of attack. It can't be too nose down, right? And it can't be too nose up as it enters the atmosphere, because it'll tumble. What that does is that gives us a very specific amount of volume of space that we can work with as the ship re-enters the Earth's atmosphere and starts encountering the mass of the atmosphere. So the ship's geometry on the face of it, I'm going to use this side, the curvature of the ship right there, along with how the rockets are going to be designed and orientated for turbulence, has to be accounted for. As the ship re-enters the atmosphere and starts hitting more and more particles, more and more atmospheric particles, the ship's going to shake and vibrate as it's hitting more and more stuff. And this brings up the idea of the golf ball. Now, the golf ball is a really interesting design phenomenon because there's all these dimples in it. And you'd think a thing with dimples wouldn't fly through the air better. You'd think it'd have more turbulence, so it'd spin differently. But in reality, without the dimples, the ball doesn't go as far, and the ball has a tendency to curve to the left or to the right and doesn't go as straight. So can this be designed into the rocket ship, those dimples be designed into the rocket ship for reentry, so that way when the turbulence happens, it smooths out the turbulence and equalizes out the turbulence around the ship as it penetrates the atmosphere. So this is a design aspect. Can the surface of the ship be dimpled to reduce the friction of turbulence coming through the atmosphere? That's one idea. Second idea, we have to understand what the composition of the atmosphere is that the ship is encountering, and then is it possible to use a catalytic material that converts the atmosphere into something slightly different, changing it like your catalytic converter would change the fumes coming out of your engine to something less toxic out the other side, without destroying the substance. So can we convert, as we're penetrating the atmosphere, can the material actually convert the atmosphere into something slightly different and not be burned off? That may have no effect. I'm not saying it would. I'm just saying, is it possible to have a catalytic effect when in contact with the atmosphere? That catalytic effect may bind more atoms together, converting into different molecules, which may interact with the ship differently. Again, that may have no effect. We may not have enough time for that effect to even be reasonable. So I'm not saying that's a good idea. I'm just saying, is it an idea? Can we have a surface that's a catalyzer to the ingredients of the atmosphere that we're encountering and convert those ingredients, possibly making a denser shield of those materials on the surface of the ship. Who knows? Without thinking about it, we don't know. Then, so we have geometry of the ship. We have catalytic surface components. 3, ablative shielding is well known by NASA, and that's a shielding layer that burns off. And as it burns off, it puts another shielding layer is now in contact with the atmosphere. And as the ship goes through the atmosphere, it gets denser and denser and denser, slowing the ship's descent down and increasing the friction and actually reducing the heat load at some point. The last time I checked, I believe it was something like 8 minutes to penetrate the atmosphere to a point where we could land a shuttle or something to that effect. I could be wrong. That's just me flying off the cuff and trying to remember how long it took a shuttle to re-enter. I don't think it's in the hours. I think it was like 8 minutes of re-entry before the shuttle got to a point where it was no longer potential to burn up. It could crash. It could still miss its target and crash, but it was less likely to burn up after 8 minutes of penetration of atmosphere. And that's due to the speed at which we're re-entering the atmosphere. If the usable atmosphere is 8 miles and the orbital atmosphere is 160 miles, something like that, and our space station's, I believe, somewhere in the 225-mile range off the surface, then the denser atmosphere where we can still fly planes and things of that nature is roughly 8 to 10 miles high off sea level. Somewhere in there, we stop the descent, the process of burning up from the 160-mile mark down to the 8-mile mark. And it only takes so much time at the speed of descent to travel down into that zone. Now, this is where the ship having the potential to slow its own descent by changing its angle of attack and then rocketing down, which sounds crazy, but just stay with me. If we can have the mass angle of attack until we get into scramjet zone where we can really throw material in and start burning it out like a scramjet or a ramjet would into the atmosphere, then we could start putting propulsion back through the rocket, and we could engage that layer of atmosphere longer, change the angle of attack so that we can slow down. We're not going down now, we're going forward, and then we can lower our angle of attack into the next layer. So as we lower our angle of attack into the next layer by changing the angle of attack to be less steep and cruise through that layer and just slowly lower our altitude under control, right? We're controlling that descent. We may still have friction on the surface that's really hard on the nose cone, but the ablative shielding would take less heat and it could cool off. And then as we reduce our distance to the Earth while still moving forward through the atmosphere, then we could get to a point where we could release those rockets and stop using the scramjets and start falling again. And it would heat up the tiles again. And then we could use the scramjet even better now because we're denser atmosphere. And we could move forward a little bit longer. And then, again, reducing our height into atmosphere, but moving forward farther. And then we can turn the scramjet off or the ramjet off and fall a little bit further and then turn it on again, and we'd be doing steps and stages of propulsion back into the atmosphere as we're lowering through the atmosphere until we got to a point where either we ran out of fuel and we had to go back to angle of attack only, or we got into an atmosphere that was dense enough to where we wouldn't burn up. It's a thought. We gotta have them. I'm not saying it's a good idea. I'm saying you have a better one. So that brings me to the shape and geometry of the ship. And it takes me to the ablative armor, and takes me to the idea that as the ablative armor burns off, it could turn into channels and fins on the bottom of the ship that would give the mast direction. And as it gave the mast direction, it would stabilize the shaking of the ship into a more stable control, just by the geometry of the ship having different curves and pockets that are longitudinal along the ship. Now, this is reminiscent of what the jets started doing, is they started putting risers on their wings, and those risers caused the turbulence to focus. And as the turbulence focused, they got less shaking in their plane. It stabilized their wing sets. Can we do that to the bottom of the Starship as the ablative shielding cooks away? Could it turn into these channels and start channeling like rocket engines? So while the ship is descending, these channels become obvious, right? And then they guide the basically the contrail of atoms backwards, and as it goes through, those get deeper and deeper and deeper, giving more guidance to the ship, acting as miniature wings. Then, as we get into atmosphere, can we use hypersonic parachutes? Knock hypersonic parachutes off to again slow down or create more drag on the ship, so that way it's not heating up so much. And those would be releasable. They'd pop out, they'd inflate to their maximum capacity. The ship would slow down. Then it'd get to a point where the rockets might be able to take over, or we release the hypersonic parachutes, and then we go to subsonic parachutes. So we release one, blam, and then we start falling again. Terminal velocity 32 feet per second. Bam! We put out regular parachutes that could slow down the descent of the ship. And again, they would be slowing down the descent of the ship, so that way the heat shields wouldn't be destroyed. Now, using parachutes could be very stressful on the ship itself, so we have to be thoughtful of that and mindful of it. And I understand that the ship weighs thousands of tons possibly, and you're going to put a huge amount of strain on it because of these basically huge parachutes that are going to start slowing it down, and suddenly. So maybe they come out as little parachutes, and then as it starts slowing them down, they start getting bigger, and they slowly pull the next parachute set out, which slowly pulls the next parachute out, and it slows the ship down in stages. Instead, suddenly, we don't want sudden changes in velocity, because the ship could rock or rack, and we don't want the ship to be doing this, because it could break the ship. We don't want that. So we want it to be stable. We want a little bit of flex, maybe, but not too much. Not too much in any direction, but because the ship is going to rock and flex and do stuff. We're talking reducing the speed so we don't burn the ship up in the atmosphere. And then there's heat shielding propulsion jets, which I've talked about before. But as the ablative shielding burns away, as the geometry of the ship becomes a stabilizing force from the ablative shielding burning away, then micro rockets that are basically canisters with volumes of either water or high density propellant would have like a copper cap on them, and as they melted, they would exude their fuel, probably water, and buffer the ship, slowing it down just slightly enough, because again, terminal velocity is 32 feet per second, so it's not a lot, but we're talking about 8 minutes of getting through atmosphere to a place where we can actually control the ship without burning up. So we only need these in stages, 1, 2, 3, 4, 5, and then we should be through atmosphere, and we should be done worrying about burning up in atmosphere. So those would be like little miniature microjets that, as they heated up, their copper nose cones would blow away, and they'd exhaust their fuel suddenly, but not a lot of fuel. We're talking a few seconds of fuel, and every second's 32 feet per 32 feet, you know. So it might only give them 64 feet or maybe 120 feet of slowdown. But in that 120 feet of slowdown, that'd be another density layer of atmosphere, because every one, you need to know how dense the atmosphere is. So we need some person to calculate the density of atmosphere from the top, where we're calling it atmosphere, to the usable atmosphere that's about 8 to 10 miles high, where we can actually control plane flight. And in those density sections, as it gets denser and denser and denser, we need to know where the ablative shielding works. We need to know where the parachutes would work. We need to know the timing at which the little propulsion jets would work. We need to know the rate of fall. We need to know our descent angle attack, rocketing through our descent angle to slow down the ship's fall by pushing it forward. We need to know if hole polarization would have any effect on polarizing atoms against it. I've talked about that before. We need to know if catalytic materials would have that effect also by forcing atoms to combine and create a denser surface of atoms on the front. We need to know if other devices like the geometry of the ship opening up would work, or changing its geometry so it's, you know, slightly fatter and slightly narrower at certain distances, causing more resistance, slowing the ship down even further. Do we slow down the nose cone by changing the shape? Do we take the whole rocket and change the whole rocket's shape? How do we change the rocket? And can we do that without causing it to burn up in atmosphere or destabilize itself and go out of control? Can we cause the wings to go out further, or have wings that are sacrificial, that go out to create more resistance? So imagine that the wings are there, and then suddenly they can go out a little bit, and then they can put out wings that are sacrificial that go out a little bit further. Again, everything that stabilizes the ship as it passes through but slows it down. More resistance, slower descent. Can a chemical be put into the nose cone that's inert, that could be pumped down the face of the starship as it's overheating, to be dumped over the heating surface and neutralize the heating surface? That would be a good question, although probably completely not realistic. And that would be tubing that would go down the length of the rocket. Then as the ablative armor burned away and the little jet propulsions burned away, then the next layer might be the tubing layer, which would exude a coolant like a liquid nitrogen or something. And that would cool the surface of the rocket as it was still penetrating. And that might only be a few seconds, but again, that could be 120 feet of penetration. That could be further and further down. So we're doing layers and steps. And if we could get another few seconds of cooling on those heat shield tiles, that would be better. Then when we get to a point where we no longer need the heat shield, can we rotate the ship and dump the heat shield? And when we dump the heat shield, could that be another parachute set? I just want to know if there's potential possibilities. I want you to do thinking on it. I want scientists to do thinking on this. We need answers, and we need them fast, because right now, Elon Musk's starships, the SpaceX starships, are not surviving launching, and they're not surviving reentry. And I'm sure they're all working on that really hard. Yet we need better results faster. One of the ones that I was concerned with is aluminum. Aluminum foil is a great dissipator of heat. So can we use materials like aluminum foil, or stainless steel tubing, stainless steel like micro tubing, as radiators on the underneath the ablative armor shielding and the heat shielding to suck the heat away and draw the heat away, so the heat shields can moderate their temperature better. This seems like a really good idea, but again, it's probably not effective for mass to weight ratio for launch, but we have to talk about it. It could be valuable, it could be devastating, I don't know, but radiators do a great job at dissipating heat. Materials like aluminum and stainless, aluminum melts at way too low a temperatures, so probably not aluminum, but stainless steel can take temperatures that would melt steel, regular steel, because of the chromium content or nickel content, and it can reflect the heat back towards the surface that's throwing the heat at it. So it's a very reflective surface for heat. There are other metals like titanium, they're very light, that are very heat resistive. So is titanium something that could be underneath the tiles also? These are the questions that we have to ask ourselves as the ship is penetrating, and at how many stages, how many levels, how much vibration, how much sonic vibration is happening in the ship that's causing it to stress. Can we reduce those internal sonic vibrations? Do we have ways to make dampeners of vibration inside the ship so it's not just vibrating itself to death? There's a huge amount of stress on a ship when it's penetrating atmosphere. Because some of the ship has got higher density atmosphere that's hitting, and some of the ship has lower density atmosphere, and it's rocking and vibrating back and forth because the density of the atmosphere is inconsistent at those levels. So as particles are hitting in pockets, the ship is rocking in pockets. And is there a way to internalize dampers inside the ship that would help slow that motion down and moderate that motion so it's not as negative to the internals of the ship? Can we change the pressure inside the ship versus the outside pressure of the ship? Can we draw air into the ship and then exit it out? So instead of having microjets out, maybe there's microjets in that actually pull air deeper into the ship but exit it out the back of the ship, creating like a vacuum. Can we? So imagine that we've got the golf ball material on the outside of the ship, and in the center of every divot there's a hole with a vacuum. So as the ship's falling through, it's got huge amounts of suction on these holes, and it's just sucking the heat and the mass of the atmosphere through these little pockets, and then ejecting out the back. Now that might cause us to go slightly faster, which might be bad. But is it possible to create a vacuum around the front of the ship so that way there's not as much mass hitting the ship until we get to a denser layer? That's a great question right there. How do we change the resistance of the surface of the ship? Can we bring the surface of the ship to zero through vacuum, micro holes in vacuum, to suck the mass away so it's not causing friction, so it's not causing heat, cause negative zone until we hit a layer where we can slow that vacuum down, or even reverse it and start pushing vacuum backwards at the atmosphere, causing the ship to slow down because it's hitting more mass of atmosphere. The vacuum one, I think, is an actual winner, weirdly enough, because we can already do that here at ground level to get better mileage per gallon of fuel on a car. So what we can do with drag coefficient, there's a drag coefficient on a car, there's a drag coefficient on the Starship too. So with a car, what we can do is we can put a membrane around the car that's got micropores in it. And as the car is driving down the road, we can pull a vacuum on that micropore structure, causing less turbulence on the surface of the car, allowing the car to slip through the atmosphere better. So we use a little tiny amount of power, create a huge amount of suction, and then as we create the huge amount of suction, we're slipping through the atmosphere because there's less atmosphere around the car. Thus we can achieve better miles to the gallon for a vehicle. So there's no reason for us to not think that the Starship, as it's coming in with its golf ball dimples all over it, that each one of those golf ball dimples wouldn't be a mesh that has vacuum attached to it and suck into the ship and then exit out of the ship a negative vacuum portion. So there's no atmosphere to encounter as it's falling until it gets to an atmospheric layer where the wings are actually encountering enough atmosphere to change its flight pattern. And as it does so, we could reverse the vacuum to a blower, and that vacuum could turn, basically turning a valve, same vacuum, different purpose, turns the vacuum into a blower, and that blows out the atmosphere, which would cool the surface of the armor, the heat shielding. It would slow the ship, maybe not much, but maybe enough. It would start slowing the ship, and it gave the wings time to start accepting the atmospheric turbulence that's going to encounter. Just some thoughts. If you like this kind of content, I need you to thumbs up it down below. If you really like this content, then you can subscribe. If you really, really, really like this content, share it with a friend. And if you really, really, really like this content, make some content of your own and share it with me, because I want to see what you're thinking. Have a great day.